Okay, so let me just first explain, even before I introduce myself, let me say why I'm doing this. This field it's a complex field. Okay, it's one of those areas of advancement in the world in technology where typically there's a huge amount of background behind it in order to understand it. And I find that when I just talk to normal people, and by normal people I mean my wife, my parents, people who don't do this kind of thing for a living, they really don't even have any idea what AI means, what deep learning means. These are great terms, but what does it mean? They watch movies, uh, they read articles about it, but that doesn't mean they have any idea of what's actually going on. It's just a kind of a big buzzword. And I thought it would be important to give a real introduction to what this is. And by that, it's a very high level introduction, but it's one that should hopefully, if you've only heard the term AI and you think magic, hopefully it will get you a little bit away from thinking that it's magic, and understanding a little bit more what you might encounter. So just a little bit of background on me. So I have a PhD in computer science, and specifically in speech recognition. So my thesis was on rapid adaptation for neural network speech recognizers. So this is something that I was doing actually back before neural networks became popular again. It's kind of fun seeing the progress in the last decade in neural networks, and it's due to some of the deep neural networks that I'll talk about briefly a little bit later on. For the last few years, I've been consulting in speech recognition and standards for the web and internet. If you've heard of WebRTC, I'm one of the primary editors of that specification for basically its technologies within HTML for getting access to cameras and microphones and doing real-time communications between browsers or other devices using that standard. I have a friend and I are starting another company, Lookout.ai. You're welcome to take a look at the site. I can't really talk about it much yet. We'll hopefully that will change within the next few months. So I mentioned movies. Many of us have seen a number of these movies. I'm going to start with one of the older ones, Metropolis. This is one where the artificial intelligence is a machine. It is a physical, gears and springs and pistons machine. But one of the interesting things about it is actually you quickly realize in that movie that the humans are subservient to the machine because they are the ones who have to keep it working. And this is something that's interesting, which I'll come back to in just a moment. I, Robot was a book by Isaac Asimov, and then there was a whole series of books from Isaac Asimov. The first one was turned into a movie with Will Smith, and it's really interesting because that was one that attempted to explore the idea of what would it mean if you had intelligent robots? How do you keep them from turning on their creators? What kind of rules could you put in place to ensure that they cannot turn on their creators? Blade Runner was interesting because it again looked at what does it mean to be human, right? And if you have a machine and that machine can act like a human, what difference is there, if any, between that machine and a human being? And then some of the more recent ones that I found particularly interesting are Her, which is it's fun entertainment, but it gives you an idea of what the future could be like once we have agents that really are more capable than human beings. So it's definitely, if you haven't seen that, it's definitely a fun one. And Ex Machina, although it's terrifying to watch, it is also, I think, one of the best ones at showing from a modern perspective what an artificial intelligence might be like. It's very possible that an artificial intelligence, a true artificial intelligence that we created, might look nothing like what we think of as human. And if you'll bear with me for just a second, I forgot I need to just mute all the microphones here so we don't get some background noise. So I'm gonna mute everyone here if it works. Nope, it's not gonna do that for me.
Muted.
To do that. Okay. And just quickly to make sure you can hear me, it looks like I'm not muted, but if someone could just type yes if you can hear me right now, just to confirm. Paul had to step away, so I'm kind of running the admin part here. Okay. I believe I'm unmuted. It would still be helpful if someone would be able to just type a yes into chat. Okay, thank you. All right. Just wanted to confirm before I continued. Okay. All right. So, you know, this is AI in fiction, right? This is what movie makers and authors have dreamed up about artificial intelligence. And it's great that they're thinking ahead. What's interesting about all of this, though, is that these are all movies that talk about AI in sort of the ideal or the general sense. So if we look at a little bit of history on what that means, what would artificial intelligence really mean? Probably the most well-known definition is the Turing test. Alan Turing, who was featured in a movie called The Imitation Game recently, actually wrote a paper called The Imitation Game. And in that, he described a game where a human being is talking with two parties. You can't see them. They're behind a screen, or behind two different screens, right? And one of the parties is a human on the other side of that screen, and the other one on the other side of their screen is a machine. And so the question was, in conversing with them, can you tell which is which? And if you cannot tell, then he would consider that artificial intelligence. The machine was indistinguishable from a human. Now, again, this is, of course, spoken, right? This is not written, this is spoken. And there's some other interesting philosophical issues and challenges with that are interesting. But it turns out that researchers in real life don't actually care about this, right? Although plenty of people care about the illusion of intelligence. So what I mean by this is that researchers are, in large part, not working on the general problem of human equivalent artificial intelligence. Instead, what they're working on is accomplishing tasks that, to date, only humans have been able to do. But that doesn't mean that they don't have fun with creating the illusion of intelligence. So humans have been fooled in the past, and I thought it'd be good and instructive to take a look at 4 examples where that's occurred. So one of the earliest well-documented such cases is the mechanical Turk. So in the 18th century, there was a machine. It was a chess-playing machine. So this is a mannequin that you see in the picture here in front of a chessboard. And this robotic mannequin is able to move pieces around on a chessboard and then indicate when someone's in check or checkmate. And so this actually showed up in Austria and then made the tour of a variety of kingdoms in Europe, and was really popular because it was not only novel in terms of what it did, but also it was quite capable. The machine frequently beat humans. In fact, well over 50% of the time it was able to beat people in playing chess. I believe it was much higher rate than that. So I have a link not only to the image, and I should point out, when I have a link to the image, those images are, of course, not mine. They were, borrowed from somewhere else. So, so you can always go and find that image in its original location. The article on Wikipedia is actually a pretty good fact-based article. about the Turk. But what's most interesting about the mechanical Turk, and you can see here with the cupboards open, right, that there's nobody in there. Well, it turns out it actually was a trick. And there was a human being inside. So this is a different drawing with a person inside controlling the movements of the mechanical Turk. So there was a man hidden in the box. There's a great Wired article from 2002 that talks about this and talks about how many people this machine really fooled. Now, the interesting thing about Mechanical Turk, and this is one of the comments I referred to at the beginning when I talked about the movies, Metropolis in particular, is Amazon's Mechanical Turk. Some of you may be familiar with this. AMT, Amazon Mechanical Turk, is named because it is human beings performing tasks that are then collected together to make it look like a machine has done them. So it is a human pretending to be a machine, pretending to be a human. And it turns out it's actually a great way for people to get some kinds of work. And it's also very useful. I've used it myself to do transcriptions of speech data, the Amazon Mechanical Turk that is. But let's face it, this is not artificial intelligence. It may be artificial intelligence, but there's definitely no machine intelligence involved here. One of the other well-known examples of this, where someone created something that was attempted to emulate human intelligence, is often referred to as Eliza. Eliza was a language that allowed for the creation of some modules or scripts that would allow it to converse in a particular domain. And if you look at this example, I only did this just a couple days ago. What you're seeing right here, this was my interaction with that particular website. So you feel free to go there and try it out yourself. So it started with Eliza saying, please tell me what's been bothering you. And I typed in, I'm worried about AI taking over the world. To which it responded, do you know anyone else who is worried about AI taking over the world? So I answered, yes, a cousin of mine. And Eliza says, I understand. So then I asked, how can I keep up with this technology? And Eliza asked, do you say, how can you keep up with this technology for some special reason? And I said, I guess I'm afraid of my company being left behind. At which point Eliza's response was, why do you say your company being left behind? So the previous question, the do you say question, was a little odd sounding, but this one is just downright wrong. No human being who speaks English decently would actually phrase a question like that. So at this point, it's really obvious that I'm not dealing with a human being on the other end. Eliza is just a clever keyword matching system. It looks for keywords, it finds nouns and verbs, and it restructures the sentence with some certain patterns to superficially simulate a human conversation. There is no actual understanding there. What's really interesting about this is that it only works because human beings are very good at inferring meaning from patterns in sentences. So when Eliza asked me, do you know anyone else who is worried about AI taking over the world? That sounds like a really insightful question, okay? And I think, wow, this is great. Eliza is going to get into something deep here. Maybe that's relevant to my problem. There's a good description, again, on Wikipedia. I'm not only pointing you to Wikipedia, but sometimes they do have really good summary explanations of things. So this one's interesting because it actually can seem like a human being for a little while before you realize that something's wrong and it's just copying you and tweaking things a little bit. Now, Siri is probably one of the most famous recent examples. People had a lot of fun with Siri when it came out. In 2010, it was an app on the App Store, and then it became part of all of Apple's iPhones beginning in 2011. The description that they gave in the announcement, and the YouTube link I have here is for the original announcement of Siri when it first came out, was that it was your intelligent assistant that helps you get things done just by asking. So it turns out that Siri was came out of a project at SRI, the Stanford Research Institute, to create a fairly natural sounding artificial assistant or intelligent agent. And it basically works sort of like Eliza, but it used a lot of statistics instead of rules. Now, there were still a bunch of rules in there. The thing that really made it unique, though, because there were other intelligent assistants out at that time, the thing that really made it fairly unique for the time was that it had really good integration with user-specific contextual information. So it had access to your address book and your calendar. It's things like that that were integrated very well into Siri. Additionally, there was a huge amount of work that went into hand-coded fixes. So I say that they use statistics, and I'll talk about that more, a little bit more later on. But there were a bunch of mistakes that the original internal version made. So I actually, an acquaintance of mine is the person who actually, well, one of the people who led that project at SRI. And he told me that there was a huge amount of hand tailoring that went into it to correct the mistakes that the statistical-based core of the system was making. So when you look at a system like this, you don't realize how many man-hours of work went into making this seem natural and seem intelligent, including all of the great Easter eggs that are available in Siri. Huge amounts of engineering to make it work. Now, around the same time frame, IBM's Watson system challenged the two longest running champions in Jeopardy to a game and won. This was well publicized. Some of you may have remembered seeing this when it happened. It was quite impressive in that, you know, it actually did a really good job in coming up with the answers to all of the questions. What many people don't realize is the work that went into it. Normally, I don't like giving a wall of text, and I despise reading text, but I'm actually going to read this because I want to be able to point out a few things. So in order to do this, IBM developed Deep QA. It's a component-based system that took about 20 researchers 3 years to reach a level where it could tackle a quiz show performance and come out looking better than its human opponents. First, Deep QA works out what the question is asking, then works out some possible answers based on the information it has to hand, creating a thread for each. Every thread uses hundreds of algorithms to study the evidence, looking at factors including what the information says, what type of information it is, its reliability, and how likely it is to be relevant, then creating an individual weighting based on what Watson has previously learned about how likely they are to be right. It then generated a ranked list of answers with evidence for each of its options. The information that Deep QA would eventually be able to query for Jeopardy was 200 million pages. So the key things I want to point out here are, it took 20 researchers 3 years, hundreds of algorithms, and 200 million pages of data in order to do this. So in order to make something that in a particular context made it look smarter than a human being, this is what was required. So when you look at all of these together, what do you see? Well, the mechanical Turk was basically a trick. The Eliza, with its doctor script, was a neat trick and some programming. So there was some programming. The neat trick was basically fooling a human being by taking advantage of the meaning that humans would infer. Siri had tons and tons of programming. And Watson was tons of programming plus tons of data. In short, AI so far, artificial intelligence is a neat trick, lots of programming, and lots of data. There is no human intelligence. There is no artificial human intelligence, even to this day. There's a neat trick, lots of programming, and lots of data. And it may seem like I'm belaboring this point, but this is something that is important to understand in order to begin to decrease the mystique of AI and this term AI that gets thrown around all the time. So what is AI today? What is touted as AI today? Well, there are intelligent assistants, which is mainly lots of programming. Okay, so again, it's still pattern matching with rules, and now we're adding some statistics in as well. And it's also machine learning. And yes, statistics are also part of machine learning, and that's what I'm going to be talking about. But many of the intelligent assistants that you see just have lots and lots of programming. And so don't be lulled into thinking that you can create a fabulous intelligent assistant just by throwing data at it with no human involvement. No one has really been able to pull that off today. There's still a lot of programming involved. But most of the work today, and most of the interesting work, I would say, going forward, is in machine learning. That's really where it's at. So I want to give some examples first of where it's being used today. Of course, we all know and hear about self-driving cars. We hear about not much because they hide it, of course, but all of the trading desks at all the major trading firms have software that do their trading nowadays, right? Nobody does it by hand. It's all very sophisticated programs, a lot of neural networks that are used in financial trading. But there are a couple of articles that I think are well worth looking at that just give you an idea of the variety of applications that you'll find machine learning used in. Yelp has a huge number of images, and they decided that the best way that they could manage that was to use machine learning to both categorize and be able to present appropriate images. Many of Pinterest's business operations actually are either handled automatically or heavily informed by today's machine learning technologies. The chatbots in Facebook Messenger, timelines in Twitter. EdgeCase has basically provides e-commerce conversion rates for customers. And they've actually, the way that they do that is through an immensely trained machine learning system that provides these recommendations and provides numbers. Baidu, which is China's China's search engine company comparable to Google, has Deep Voice, their project, which is has one of the best speech recognition accuracies on the planet today. It's a machine learning application. Salesforce, their Einstein is as well. There's another great article here. Kaspersky Lab, their antivirus program, uses Deep Instinct, and it's because basically it's a machine learning program, because when new viruses come out, they never look exactly like existing ones, but they do often look similar to existing ones. So they figured out how to develop and train a very sophisticated system that looks for patterns of behavior in code that are virus-like in order to find new viruses that it hasn't seen before. There is Medicision has a patient hospitalization prediction that they can make for diabetes patients. That's pretty sophisticated, and it's not a human being doing it. Legal Robot does contract analysis, fraud detection. All the major financial companies use some form of automated fraud detection. PayPal has talked about their system and what they use in terms of machine learning to do it. Breach detection, customer support, legal research. As you can see, there's just a huge variety here. So I've talked a lot, I've set all of this up, but I haven't really talked about what any of it is yet. And so now we're going to start looking at that. So machine learning today falls into one of two categories. So the technologies that are used fall into one of two categories. They're typically either model-based or they're a general classifier. And I'm going to talk a little bit about statistical estimation, which is probably the most common core piece for model-based technologies today. And then I'm going to talk about general classifiers in general and focus a little bit more on neural networks. So your real-world problems would require too many rules. So if you think about Eliza was great. It was all rules. Okay, it said if this then that rules. But real-world problems have too much variety, too much flexibility in them for rules to work. So one of the ways you get around this is by using statistics. Statistics generalize using data. So instead of creating a rule, you use existing data and you come up with statistics from that data and you use that to drive your decision. So I want to talk about that first. This is a chart that shows heights of human beings. It's actually human females. And so ignore the red curve for a moment. If you take 1,000 people and you ask what their height in meters is, and then you put them into bins based on, at a centimeter level, then you'll get a chart that looks something like this, okay? Where the majority of the human beings you're seeing here are at 1.6 meters, but of course, they're concentrated in the middle of this block, and then the heights tail off as you go lower and higher. Now, this set of boxes, if you do this with more and more and more and more and more people, you will end up getting something that looks, as you get smoother and smoother, these boxes get narrower in width, you will begin to get something that looks a lot like this red curve. And this red curve is a normal distribution. I'm not going to go into detail on normal distributions. There's a lot you can find online about what a normal distribution is. But interestingly, human heights are normally distributed. Now, something that makes this a little bit more complicated is that, I did cheat here. I only showed you human heights of women because it's not human heights that are normally distributed. It's human heights by gender. So what I'm showing here is the same thing, except that now we're looking at height in inches, but we're showing there are two different distributions here, two different groupings by women and by men. And you can see that they're actually quite different if you look at them. Of course, women on average, are shorter than men. But what you can see also from this is that there's greater variety, there's greater width in this distribution for men than for women. So you're going to find more men, proportionally speaking, who are farther away from the average than you will women. But the key here is that in order to be a little bit more precise, we've now introduced two normal distributions, right? One for women and one for men. Well, if you actually want to predict human height, to get the best results, you don't want to just look based on gender. It turns out, so I went looking to see what are the factors that correlate well with height. So if you normalize for these factors, you actually get better results. The country that you live in is strongly correlated with height. Of course, your mother's and father's heights and your age, obviously, right? If you're a child, because what I showed you before was heights of adults. Definitely, of course, if you're a child, your height will be different. So the point is that to get good results here, you actually need multiple models, multiple distributions in order to get a good result. So there are a number of technologies, a number of solutions today that use statistical estimation. Almost all natural language processing today uses some form of statistical estimation. All of your chatbots, all of your search engines, all use statistical processes and statistical estimation. And in fact, all speech recognition engines, all voice recognition engines in the 1990s and early 2000s used statistical techniques almost exclusively. There was some work with neural networks, but not a lot. That's changed, of course, and that's what I'll be talking about in a little bit. Listed at the bottom here, some technologies that you may actually come across these. You may find someone who uses the term maximum likelihood estimation, or MAP estimation, or GMMs, or HMMs. If you see any of those, what they're talking about is statistical estimation, exactly what I just showed you. Collections of normal distributions. Or I should say, estimated normal distributions. And in fact, that's one of the problems with statistical estimation. So most approaches make use of normal or Gaussian distributions, but of course, not everything in the real world is normally distributed. One of the ways that we get around that, as I just showed before, is that you just use more of them. Okay, so in the case of human height, the more variables we can find that are relevant, the better precision we're going to get in our estimate of what a particular human's height is, right? If we think about our original chart, right, that just had one normal distribution, well, from that, if we had to make a prediction for what your height was, we would pick the average, and we would, for any person, we would guess just the average. Well, once we were looking at separating it by, women and men, then we would at least have two different estimates. Female, we're going to give you a different estimated height than if you're male. Still terrible, right? Because there's huge variability. If you're female, you're not all the same height. Okay. So the more of these distributions you can get for the specific case that you have, the better your estimate is going to be. Unfortunately, it takes data to create these estimates, and the accuracy worsens the more models you have. And what I mean by that is the total amount of data that you have, if spread over 20 distributions, will be more precise for those distributions than if you have 10,000 Gaussian distributions or normal distributions that you're trying to estimate using that amount of data. Okay, so when you reduce the data available per distribution, you reduce the accuracy of that specific distribution. And as we know, statistics are really only valid in the aggregate. If you try to compute some kind of statistics off of 5 examples, they're going to be terrible. You're going to need a lot more than that. So people have been wondering if there's a better way. And by the way, lots of work has gone into using statistical distributions and trying to overcome some of the shortcomings that I just described. So they're pretty darn good, but they still have some of those problems. Well, recently there's been a lot more success with a variety of other classifiers. So I just wanted to talk about a general classifier before I move into talking about neural networks. So instead of explicitly creating a model, you could consider using a general classifier, where a classifier just maps some set of inputs to a class, an output class. Maybe you have 3 different output classes, and so whatever your input variables are, it just figures out a mapping from that to that output class. So there are 2 main types of general classifiers that are used today. One is some sort of clustering, and the other is artificial neural networks. This chart's a little busy, so bear with me for a moment while I explain it. And start by just imagining that you don't have any of the colors on here. You only have the symbols. So if you notice, on the left side, you've got triangles. On the right side, you've got circles. And in the middle and towards the top, you have pluses. So those represent some particular data set, okay? And you have 2 different components here. So think of these as 2 different variables. There's the X variable and the Y variable. And those data points basically show, so for the plus, everything that was actually in the plus category, we have, well, a plus means a particular category, a triangle means another category, and a circle means another category. So the question is, if you see something new, a new sample comes in, and it has a particular value on the x-axis and a particular value on the y-axis, that's going to place you somewhere on this chart. But then is it would you classify it as a circle, a plus, or a triangle? Well, in this particular case, we're using ellipses, rotated ellipses, as our classifier. And we're just saying we know that there are 3 different classes we care about. So we're using some kind of tool that, that tries to fit ellipses to the data and tries to fit 3 ellipses to the data. And so I'm showing here a sample learned assignment of ellipses to the input data. It's pretty good if you look at it. So most of the triangles end up in that blue, most of the pluses end up in the purple, and most of the circles end up in the red or orange on the right. But it's interesting, if you look, there's a place where the orange and or red and purple overlap, and there's a place where the blue and purple overlap. And in fact, we have some existing samples there that actually occur in both. There's a, I actually can't tell whether, I think it's a circle. There's a circle that is right on the edge of the red, but that's also definitely within that purple region. And when you have an overlap, you have a problem. You don't really have an answer. So although this is great and it would work for a very large number of our cases, it clearly wouldn't work for all of them. But the key here is that these clusters can be determined automatically using some kind of error measure. So you give it the input values, which are X and Y, and you have output classes, which is plus, triangle, or circle, and you use an algorithm that fits ellipses to the data. But I really didn't want to talk about that more than that now, because I really want to get on to neural networks. So artificial neural networks are a general purpose classifier. They don't specifically do ellipses, they don't specifically do Gaussian distributions, they don't do any specific thing. They actually can create quite complex decision boundaries, as they're called, between classes. They actually turn out to also be a general purpose function estimator, and that I'm going to talk about that in a moment. That's one of the reasons why they work. They were inspired by the functioning of neurons in the brain. So I'm going to give the same kind of diagram that everybody gives when they're first talking about neural networks, which is to show a real neuron and an artificial neuron as we use it today. So a real neuron in the brain, as we see on the top of this picture, has, there's the cell, which has a nucleus, and right there around the nucleus of the cell, in that cell body, there are dendrites that stick out. These essentially are receptors. They receive inputs from other neurons. The inputs that come in, these are neurochemical, electrochemical impulses that get sent in. They cause changes in the cell body that cause a particular neurochemical, electrochemical reaction in the axon of this cell. It's what you see traveling off to the right. And that gets spread out into what are called terminals. And those terminals, I'm not showing them here, but they're up against the dendrites of other cells. So approximately speaking, we could try to model this by having on the bottom here a variety of inputs that come into something, okay? Something happens with those inputs, and then some output is created. And that output then will become inputs into other cells, other neurons in our artificial neural network. So let's look at pretty much a stereotypical diagram of how a neural network is structured. On the left here, I'm showing input features. So this is just like we saw before, right, on that previous slide, except I've got, 6 different input features, and these could be, mother's height, father's height, age, etc., right? And on the right, we have our output classes. These are the specific, I probably shouldn't have used height inputs on the left because I don't have great classes for the output on the right. It would be better, let's talk on the left for features. Let's say we have X and Y, okay, like our ellipse diagram. And then on the right, our classes are triangle, plus, and circle, although I'm showing 4 here. The point is that it figures out, the neural network is going to figure out a mapping from input features to output classes. And the way it does this is by having one or more so-called hidden layers. And this is a set of neurons that are like the inputs and like the outputs, except that we don't set them. They're set by the network. And in fact, they're computed, it turns out. So if you look at the top value in this hidden layer, the top neuron, its value is computed by taking the first input times a weight, plus the second input times a different weight, plus the third input times a different weight, and so on, summing them all up, running them through some kind of nonlinear function that gives us an output value. And then that output value is available for the next layer, the output class here, where it will take, an input from each of the hidden units multiplied by its weight. So there are weights that go from the input layer to the hidden layer, and there are weights that go from the hidden layer to the output layer. And notice that they're unique, right? There's an individual weight for each pairing. There are some topologies that combine these weights together, but in the general sense, this is how it works. So this is called a feed-forward neural network because the inputs come in one place, they feed to the next layer, and they feed from there to the next layer. They only go in one direction. It is possible to have something called a recurrent neural network, where some of these neurons, their outputs feed back into the same network or a different earlier neuron. But for the most part right now, I'm just going to be talking about feed-forward networks. Okay, so you've probably heard people talk about deep neural networks. One of the things that happened in the mid-2000s was early to mid-2000s was some real progress in being able to handle deep neural networks. And deep neural networks are ones with many, many, many hidden layers. We're talking hundreds, perhaps, of hidden layers, where each layer may have hundreds or thousands of nodes in them. So one example is the ImageNet challenge. So ImageNet is a collection of a huge number of images from the internet. And every year they have a challenge that they put out for classification of the images in their database. So one of the common data sets, it has 1.2 million training images. They have way more than that. But one of these challenges used 1.2 million training images, which had to be classified into one of 1,000 different classes, each one. Recent winning systems, neural networks, had approximately 60 million weights. Okay, so in this diagram that we have here, imagine 60 million of those crossing lines. All of those have to be estimated. The values of those have to be estimated using that training data. And it took many thousands of training iterations in order for those weights to stabilize to something and give a result. Another example is Go. So AlphaGo in 2016. Go is a 19 by 19 board. In this particular case, there were 28 million training examples, and they had more than 10 million weights in their particular neural network. In fact, they had multiple neural networks, so there were more than 10 million weights in each one. Some of these networks trained for more than 340 million iterations, just to give you an idea of what's involved to actually train one of these systems today. Okay, massive amounts of data because there are massive numbers of parameters, and they train for a very long time. So these are big, okay, and they're complex. And I want to just say this is going to be brief, and I apologize for that. It takes a lot to explain this in detail, but I do want to give you a sense of why neural networks have succeeded. Why is it that neural networks, deep neural networks, have taken off so rapidly? The output for any of the neurons in that network that I showed you is a function, usually a nonlinear function, of all of its input nodes, right? I said that you take the input times a weight plus an input times a weight, you add all those up, and then you run it through a nonlinear function, okay? So any particular neuron's value is a function of its input nodes, and the weights too, of course. So the output nodes at the very end, those output classes, are a complex function of the raw input vector values. Okay, so there's some really complex function that's being calculated on the input values to get you your output value classes. The only way this is feasible is through calculus. The chain rule from calculus basically says that you can take a change in, I still haven't come up with a great way to just say this in 10 seconds, but basically, if you have a function z that is a function y that's a function of x, you can figure out how a change in x changes z by figuring out how the individual pieces change. So how a change in x changes y and how a change in y changes z. So in other words, you can find out piecewise changes in order to figure out the overall change, or you can reverse it. So if you know what your inputs are and you know what the outputs are that it gives you, you can figure out how much you want to change the output. And when you know how much you want to change the output, you can figure out how much each of the individual weights needs to change in order to make that output be what you want. This is the magic of neural networks. It's that there's this very complex function that can be estimated using only very simple, many simple estimations. And neural networks can learn any arbitrarily complex mapping from inputs to outputs using this. So for those of you who prefer pictures, I have a picture here. So this is our same picture. And what I just said can be described like this. The chain rule tells us how much a change in one particular weight will change the output and output value. In fact, for each of the output values, what change in the weight would be needed. So if we have a particular output value that's 0.7, and we know that we want it to be 1.0 when it sees this particular set of input features, we know how much to change each individual weight. This is how a neural network learns a ridiculously complex mapping using a ridiculous number of simple operations. So the point is, they're all very simple operations, and in fact, they are very amenable to parallelization, like on modern CPUs and GPUs. So even though the operations are simple, the creation of these networks is not simple. There's a lot of experimentation required. Figuring out what the optimal input values should be. I mean, what do you give as inputs? Should they be normalized a certain way? How many layers? What are the types of layers? In other words, what are these nonlinear functions that you use? How many nodes do you have in each layer? How fast do you adapt them? Because you're going to make small changes to these weights each time you see an input, a very tiny adjustment. But at some point, you're going to need to stop making those adjustments. You're hoping that it's going to stabilize. So typically, you reduce the adaptation rate over time. And on top of that, doing all of this requires an absolutely insane amount of computation time and computation power. So it takes a long time to train these and experiment with these. One of the reasons I want to point this out is that when you read a paper or you read any description where someone says they're presenting results and they say, we tried these 3 neural network architectures and these are the results that we got. What they don't tell you is that they actually tried more like 10,000 neural network architectures, and they're only reporting on the 3 that showed something interesting. That's something that's very important to understand, because I think people sometimes have an idea that if you have data, you can just kind of dump it into a neural network and you're done. Well, yes, but there's a lot of experimentation required to figure out what the right neural network is and what the right inputs are and all these other so-called hyperparameters. And so there's a lot more work. It's not just that you have one final architecture and you just have to train that one architecture. No, when you're done, that's the only architecture you have to run your inputs through to get an answer. But to figure out what that architecture is takes a huge amount of experimentation. but the returns are worth it. And I'll give you some examples in a moment. So model-based approaches are really good at capturing the most common cases, but they're not so good at distinguishing, at dealing with the goats. So in the speech recognition space, voice recognition space, which is my background, we often referred to outliers as goats. So, you know, if you're one of those people for whom that thing can never understand what you say, then we would call you a goat. And I actually was never sure where that came from, so I looked it up. And it comes from something in the Christian Bible where people are separated into sheep and goats. And when you hear, if you hear speech recognition researchers talk, when they talk about sheep, they're talking about the ones who are mapped properly, who are captured properly, recognized properly by the speech recognizer. And the goats are the outliers. Neural networks efficiently capture both the most common cases and the outliers. They're very efficient at doing both. Those outliers are where the statistics are poor, and that's why the model-based approaches have trouble. So before I finish up, I want to just give you an idea of what the results are from doing this. So in some tasks, neural networks today actually exceed human performance. In 2013, someone actually trained networks to play Atari games, and came up with neural networks that were better at playing them than humans. The ImageNet classification that I described in 2015, and actually since then. In 2016, I mentioned the Go. It was previously estimated that that would be a decade away before someone would beat a human being in Go, and actually in 2016 that happened. In 2017, we got a neural network that could actually classify skin cancer better than human beings can, more accurately than trained doctors. And we got a new Go game that was trained without using human-chosen training examples. So when I said before there were 28 million training examples in the 2016 Go game, that was humans selected those examples to be the ideal ones. Now, without any human-chosen training examples at all, it won. Actually, what it did was it used the 2016 Go game to play against, and then it got better than that game and is still better than humans. So there's this fabulous article I came across where the authors asked a number of experts in AI when they thought that AI would exceed human performance. And the general consensus was that machine learning would, in 45 years, machine learning would be able to accomplish all human tasks. And that within 120 years, all human jobs would be 100% automatable by machines at or better than human beings can do. So this is going to seem like a rapid end, but this really is the question, okay? Are you going to be the innovator, or are you going to be left behind? This is what I have to talk about today. This is it. So all I'm going to do is, this is sort of the one sales pitch, which is that you know, I and others at Starweaver can provide additional deep dive training on the basics of machine learning. So like today, but much deeper. And then also specific training on deep neural networks for deep learning. So actually go into detail on what are the different networks, you know, convolutional neural networks, recurrent neural networks, how you select features, how you design neural networks. We can provide additional training on that. And the goal here is to help you understand your options. So when you go to someone who's selling you AI expertise and tools, you know what they're really providing to you. Are they just blowing smoke? Or do they know what they're talking about? And even if they know what they're talking about, you know, you really need to be able to understand just what the complexity is that they're dealing with, and why they might say it takes that many data samples, or why it might take that long to train. At this point, I'll go to questions. So let me switch over here and see if there are any questions in the chat. If you have any questions, please type them in. We have just a few more minutes left. So probably some of you are typing now. Okay. What is the difference between deep learning and machine learning? Okay, machine learning is the general topic. Machine learning means any kind of learning using data and algorithms. So, for example, I described general classifiers. General classifiers can be, like clustering. Okay, so clustering is an approach that's different from a neural network. Deep learning typically means deep neural networks. Okay, when someone says deep, they're usually talking about deep neural networks because it wasn't until we started getting neural networks with hundreds of layers and thousands of nodes at each layer that we started seeing these kinds of performance gains. And that's as a result of both increased compute capabilities, faster computers, GPUs, and so on, and also some improvements in the training algorithms. But typically when you see deep, it's specifically referring to neural networks even if they don't say it. That's a great question. Any other questions? Okay. When do I think we can achieve general AI? Oh my goodness. Okay, well, I'll tell you, I have my own ideas about how to create real, what I would call artificial general learning machines. So, real artificial humans or whatnot. I haven't had a chance to work on that yet directly. It's different from what everybody else is doing today. So yes, I'm ambitious enough and audacious enough to say that I think I know a way to do it. But actually, even if I'm right, and even if I had all the computing resources I needed today, I still think that I would be hard pressed to create anything as sophisticated as a cat or a dog today in terms of intelligence. I would be thrilled if we could create something that did what a 1-month-old baby could do. I kid you not. But I do believe that the techniques to do general AI will be developed. I personally think that they're going to be developed within the next 10 to 20 years and developed to the point where they work. And after that, it's just a matter of data and computation. Okay? So does that mean that we have general AI in 10 years? No. I don't think we're going to have general AI in 10 years. I think what we're going to have in 10 years is the tools and techniques to build general AI. But it's still, computation-wise, it's still going to be another 10 to 20 years beyond that before we start seeing something that we would consider real artificial intelligence. We will not see human equivalent intelligence, probably still for, well, I don't know. We're talking, I don't think it's going to happen. It's not going to happen in less than 20 years, I don't believe. I actually think it could happen for one computer in my lifetime. Okay, and I'm not quite 50 yet, but I'm close. So I think that before I die, we will see at least some large computer capable of what human beings are capable of. And then, of course, it's just a matter of compute power beyond that before it starts being something that can fit in a room and something that can fit on your desk and something that can fit in your hand. Let's see, what companies are creating or have the potential to create major breakthroughs in the AI field? Let me just a second. What companies are creating or have the potential to create major breakthroughs in the AI field? What companies are creating or have the potential to create, okay, same thing. So, so unfortunately, today, for the most part, it's just the big entities. And that's because of the computing power. So if you look at, you know, the Googles and the Baidus and the IBMs and whatnot, I think I said computing power. That's not exactly correct. I think there are two. It's data and computing power. So any company that has access to the data has an ability to do this. As any company that has access to the computing power has the ability to do this. So there is some work beginning. I wish I could quote someone. I do remember hearing there are companies that are trying to create very large databases of publicly accessible information. And it is so that others can do this as well. Okay, so these large companies will always lead because they have the resources to do this. But it is but over time, I think we're going to start seeing data sets be made available to others as well. On top of that, I think we're also going to see compute power get cheaper. It's already possible to buy a super powerful GPU, one of the most powerful there is, from NVIDIA for $1,200. And with that one GPU, you can create a neural network speech recognizer for your data set. Okay, so that's pretty impressive. Now, that speech, vision is more challenging. It requires more processing. There are going to be other challenges beyond that as well. But I believe that many of the tasks that people are putting machine learning to today can be accomplished with one or a small number of really powerful GPUs. So again, in answer to your question, the big companies today, in terms of potential, I actually believe once the tools get easier to use, everybody can. Until then, what you need is, you can probably buy the compute power you need today. It just depends on whether you have a team of people who can collect the data and you have a team of people who can do the experimentation work that I described. Okay, so I actually believe that medium-sized companies have the opportunity to do this today and not just large companies. And with that, I'm going to have to end. We're at the end of the hour. Thank you very much for joining me today, and thank you for the questions.